Hello everyone, my name is Zhenchang Su from University of Connecticut. Today I'll be presenting Aggregation, our system for accelerating distributed communication by moving aggregation and broadcast operation into Linux kernel using eBPF. Broadcaster and aggregation are two fundamental communication primitives in distributed computing. In distributed ML, including TensorFlow, PyTorch, and federated learning, workers are constantly synchronize gradient through aggregation and receive updated parameters through broadcast. Every distributed ML framework implement or reduce, which aggregation followed by broadcast. In big data, frameworks like Spark and MapReduce rely on software operation, which are essentially broadcast plus aggregation, and these operations are bottleneck. At 10 gigabytes per second networks, communication can dominate ML training time. Software is the major fraction of MapReduce job time. The key point is that these two patterns, one-to-many and many-to-one, are so fundamental that optimizing them will benefit virtually at all distributed systems. So we ask, where exactly does this overhang come from? We instrumented the entire packet path from sender to receiver. On the left, you can see our detailed latency breakdown. The sender sign takes about 17 microseconds, with 12.3 for the user to kernel transition and 4.6 for kernel stack processing. But the receiver sign takes 65.6 microseconds, 4 times slower than the sender. This asymmetry comes from receiver side complexity, interrupt handling, packet validation, buffer allocation, and memory copying. The key observation is that overhang is dominated by user kernel crossing and stack traversal, not the network wire. In a data center, network propagation is just a few microseconds, yet the processing overhang total over 82 microseconds. The bottleneck is clearly in the software stack. This tells us exactly where to focus on our optimization efforts. This overhang doesn't just affect individual packets. It compels with scale. For broadcasting, the sender must transmit one copy to each receiver sequentially. Within N receiver, and the sender pays 60.989 microseconds N times, serialized as single node. For aggregation, it is reversed, or sender message conversion on one aggregator, and the aggregator pays 65.6 microsecond receiver overhead for every incoming packet, with N senders that accumulates to N time, 65.6 microseconds at a single point. The problem scale linearly with class size in both directions. This motivates our core idea. If we can process packets before they traverse the full network stack, we can eliminate most of this overhead. The traditional approach to this problem is a trade-off. You either use standard network sockets, which are easy to deploy, but pay the full kernel stack penalty, or you bypass the kernel entirely. RDMA gives you the lowest latency, but requires the loosest network fabric with priority flow control. Under conjunction, ROCE performance degrades significantly, and the PFC can cause head-of-line barking, or even deadlocks. It also only works within a data center, so for geo-distributed setting, like federated learning or edge computing, RDNA is simply not an option. DPTK gives you low latency with standard hardware, but it burns the dedicated CPU cores, making it unsustainable for multi-tenant cloud infrastructure, where CPU is shared. So the question we ask here is, can we get significant speed up on commodity hardware without requiring loose-list fabrics and dedicated resources? Our answer challenges conventional Winston. Instead of going around the kernel, we go into it. Modern Linux kernel provides a programmable hooks through eBPF, which let us run safe, verified code at different points in the network stacks. As you can see on the right, we attach in the two key hooks. XDP, at the very bottom near to the NIC, handles aggregation by processing incoming packets before they even reach the device driver. TC, the traffic control hooks, handles broadcast by cloning packets on the egress path. By processing at this earlier hook points, we skip the expensive network stack and socket layer entirely. The result is performance approaching kernel bypass with the deployment simplicity of standard networking. No special hardware, no dedicated cores. But there's a catch. eBPF get us kernel programmability, but with several constraints. Programs are verified for safety before loading, and which is great for stability, but imposes strict limit. First, a 500 terabytes stack limit. Second, no floating-point arithmetics operation because the kernel forbids it. Third, stateless execution within limit map memory. And fourth, a strict verifier that rejects anything it cannot prove safe. These constraints fundamentally invalidate all traditional protocol design. We cannot just port existing aggregation or broadcast the implementation into eBPF. We need to fundamentally rethink how to build these primitives from scratch. Okay, let me walk through these two hardest constraints and then show how everything comes together in our system design. The first challenge is the stack limit. Each eBPF program gets only 512 bytes of a stack for local variables. But to aggregate the package payload, we need to iterate over the data element by element. And the standard 100 bytes MTU packet contains far more data than we can process in a single function call. Each function can handle at most 256 bytes before running out of stack. Our solution is tail-call chunks. We split packets processing into chunks of 256 bytes or less. Each chunk is handled by a separate eBPF program, chained together using BPF tail-call. As shown in this diagram, program 1 processes the first 266 bytes, tail-calls program 2 for the next 256, and so on. Yeah. This effectively allows us to aggregate the arbitrary large payload within the eBPF constraint by chaining programs together. The second challenge is that ML gradient aggregation requires floating operations, which eBPF completely forbids it. Rather than falling back to user space and defeating this whole purpose, we use edge quantization. On the standard side, we multiply float variables by 10 to 8 and convert to the 32-bit integer. The kernel performs the pure integer aggregation. The receiver divides by the scaling factor and the worker count to recover to original flows. Now, Let me show how these solutions come together in a complete system. Aggregation has the three main components. First, a user space runtime library that provides a simple API with three calls: broadcast, send aggregated data, and get aggregated data. Application integrate within just a few lines of the code. Second, in kernel broadcaster attach the TC hook. The eBPF program clones the packet use BPF clone redirect and use an index mask to select the destinations or in kernel space. Third, in kernel aggregation attached to the XDP hook. Processing packet right at the NIC level. It supports some predefined operations like sum, max, mini, average, using the telco chance and edge quantization I described before, and delivers result to the user space through a ring buffer. We evaluate Aggregation at Kernel Cloud. Importantly, our baseline is not naive socket. We use some optimization method, UDP, and it's well-turned traditional approach. For broadcaster on the left, you can see with 9 receiver, Aggregation achieved 82.8% average latency reduction. Going from 534 microseconds down to 92. Yeah. For aggregation on the right, at 512 megabytes, Aggregation achieved 3.9 times the throughput of the baseline, reaching 212 million ops per second versus 55 millions. This performance gap widened with large data size, and kernel-based processing eliminates the memory copy and context switching overhead that increasingly burden user-based processing. We also evaluate Aggregation into real-world application scenario. First, parameters with 3 diverse models from vision, text, and audio. The Aggregation reduced the gradient aggregation time by up to 56.1%, specifically for the audio model with 10 works. And for the map reduced on the right, we run words counting with varying numbers of mapper and data size. Aggregation reached 257 million words per second with 10 mapper and 10 million words compared to just the 5.9 million for the baseline. This large gap are raising because the word counter reduction is computationally simple. So the bottleneck is entirely in the communication. To wrap up, Aggregation demonstrate new direction for distributed communication. Constrained kernel programming rather than kernel bypass. We show that eBPF several elimination actually drive innovative protocol design. Telco chance solve the memory problem. Edge quantization handles floating point in the integer-only kernel. Each of these techniques is applicable before eBPF to any verified or resources-constrained execution environment. This result are substantial on commodity hardware. 82.8% broadcast latency reduction, 257 million words per second in map reduced versus 5.9 million for the baseline. And our key takeaway is that several constraints can drive innovation rather than limit it. The restrictions of eBPF forced into simple, more predictable protocol design with automatically safe guarantee, and the performance number speak to themselves. Thank you. If you have any question, please feel free to contact me.